Okay, hi guys, good evening. So we were doing coordination compounds. We just have little more things left, and then we'll go for the next chapter. Right. Okay. So we completed crystal field theory. We saw how to do the IUPAC naming, right? So and then we saw how to decide the stabilities of different complexes, right? So what is left out is one important topic, and that is organometallics, or it's also called as organometallic compounds, right? Okay, so I think from the name itself you'll be able to understand what do you mean by this, right? So what you have to understand is I should have a metal, right? Now that should be attached to a carbon fragment, right? That should be attached, it can be anything, right? So that should be attached to a carbon fragment. Okay, so like we will look into how the bonding structure is, how the bonding happens, like what are the different types of what is that, organic metallic compounds and all that. But before that, I wanted to answer one question. We have already seen one important organometallic complex. Can you tell me what is that?
Grignard Ridge.
Yes, right. So that is a Grignard region, obviously, right? It's you can see that here. I have oops, open the new one unnecessarily. Okay, fine, issues. Right. So one thing is this RMGX, right? You see, this is magnesium. It is attached to a carbon fragment, right? Okay, so that is one thing. Now this what is that? Your organometallic compounds can be divided into two types, right? Or actually three types, right? First one is sigma bonded, the other one is pi bonded, and the third category would be sigma plus pi bonded. Okay, so now you see, if you see that the interaction between the metal and the carbon atom is going to be purely in terms of sigma bonds, is that if it's going to pi bonds, it is going to be pi organometallic compounds, and sigma plus pi, we will see what is that. Okay, right. Okay, so giving you examples. Okay, other than that, I have ionic, right? Ionic compounds. Actually, this can be regarded as an ionic, but sometimes it is considered a sigma complex also. But again, you don't have to worry about it. So if I have to give you a proper inorganic complex, ionic organic, ionic organometallic. Say if I have R minus Na plus, say something like C6H5 Li, right? Li plus, this is minus. So all these things comes under your ionic type of organometallics, right? So if I go for sigma bonded complexes, say sigma bonded complexes, example can be only sigma bonds, right? Say for example, if you have I don't know whether you have seen this. Say for example, if I take AlCl3, right? So AlCl3 can be converted to AlCH3, right? And obviously it is going to exist a dimer. It is going to be in the form of this, because we know it aluminum can act as a Lewis acid, right? So if you look at the structure of this, I'll have maybe second, I'd say I'll have aluminium, another aluminium, CH3, CH3, say CH3, another CH3, and CH3. So this dotted lines which you see here indicate that these two methyl groups are attached, both this to this aluminum and as well as this aluminum, right? So anyways, what you see here, what is important is you see this is a sigma bond. Everywhere it is just sigma bonds, whatever you have here, right? So those kind of complexes comes under sigma bonded organometallics, right? Okay. So now if I go for pi bonded complexes, there are like pi bonded complexes are the most important ones. Okay. So if I look at pi bonded complexes, okay, if you're taking this down, right? Say I should have exclusive pi bonds only, right? Say all like there are some class of compounds called as metallocene, right? So these metallocene are what are called as sandwich compounds, right? right? So there are like actually there was a scientist who was awarded a Nobel Prize for the synthesis of this sandwich compounds. That guy is known as Wilkinson. So you must have heard Wilkinson's catalyst, right? So that scientist, actually, people when you ask him, they say that he got Nobel Prize for Wilkinson catalyst, but it's not. Actually, Wilkinson got the Nobel Prize for this metallocene sandwich compounds, right? Okay, so if you look at the if any example, if I have to give you, right? So if I look at, for example, ferrocene, right? So ferrocene, I can tell that metal here is going to be the iron, right? So you can even have um, uh, it's called mangosine, like that. You can have different elements coming here other than iron, right? So how this looks is that I have an iron which is sandwiched between, right? So if I have to draw it properly, right? So you are going to say first, okay, we'll come back to this. Okay, so what do you mean by these two structures I wrote here? Is a cyclopentadienyl anion. We write it as CP. That is the abbreviation. CP is cyclopentadienyl anion. Right? So if you look at the structure, I have one negative charge and about double bond and a double bond. This is the structure for cyclopentadienyl anion. Okay, right. So what you see here is this is going to involve in resonance, right? This negative charge, the pi electrons, all these things are going to involve in resonance, right? So you will end up with a structure like this, right? So like this, if I want to write the structure, it's going to be like this. This is how I write. Okay, so what do you mean by this? That means all the 5 electrons are there in the form of in the form of 5 electrons. All the 5 electrons here, right, are actually coordinating to iron. Okay, all the things are coordinating to iron. That is 5 electrons here. 5 electrons from this side, 5 electrons from that side, right? So I can even have some compounds like this. I can have a metal. Say if I have an alkene. Say now this can be bonded like this. This is an alkene, CH2 double bond CH2. Again, the pi electrons are involving here. Say I can even have something like this. Say I write it like this. So what do you mean by this is something like this. I have basically an allyl group if I have, right? So this metal is bonded with the allyl group. But what you can understand is involved again in resonance, right? So I'll be able to write it like this. Between these two carbons, the pi cloud is resonating, right? So all these are examples of your pi complexes, pi organometallic compounds, right? You see exclusive pi bonds, and you saw in case of Al2CH 6 times, that was purely sigma bonds. Okay, right. So now what comes under sigma plus pi? Any metal carbonyl, right? Any metal carbonyls, all metal carbonyls will come under sigma plus pi form a type of organometallics. Now, why am I saying that it is going to be both sigma and pi? We'll try to understand that. Okay, right. So there are no questions till now. Right. Say now any metal carbonyl, say if I have FeCO 5 times, whatever it is, right? Say I will have Fe, all are COs. This is a trigonal biopyramidal geometry, right? So now what you see here is only sigma bonds, but what you can understand is, guys, if you look at CO, right? If you look at CO, carbon monoxide, like you see that one of them is going to be a coordinate bond, right? Okay, so it can be a normal sigma bond where carbon and this attacks, right? Or I can have lone pair on the oxygen, and that will be able to have a bond with a metal. So there are two types of possibilities. So one with like this, or the other way is that you can have something like this. Okay, so like both these structures are proven to be right? Both the sigma structure, this is a sigma structure, this is a pi structure. Both these structures are proven to be right, and that's why we call metal carbons alone as a special category, coming under sigma plus pi category. Okay. Now, one more thing also can happen, right? Now you see, this is a sigma bond which is forming here, right? What I can understand is it is not only that carbon will be able to donate electrons or oxygen will be able to donate electron. I can even have metal donating electron to the carbon. That is also a possibility, right? Now, how will I bring this picture? Now you have to go for the molecular orbital theory, right? So what you see here is I have this pi star orbital of carbon is empty. Okay, pi star orbital of carbon is empty, right? So if I have any extra electrons in the metal, right, that can be donated to the pi star orbital of the carbon. Okay, so that is one way of looking at it, right? But you really don't have to worry about what to say. You really don't have to worry about how the bonding happens. That is not important to you, but you can just know it, right? So either you can have dz squared or dx squared minus orbital of the metal to be empty. So I can have a coordination from the carbon to the metal, or the metal has so much of excess electrons and metal to the carbon, which is going to have the pi star empty, that can also be a donation. Okay, right, fine. So that I wanted to tell you. And questions, if it comes, maybe it can be from the classification, or it can be regarding the stabilities. Okay, now, okay, I forgot to tell you one more thing. We saw the very reason that carbon CO as a ligand is a very strong ligand, strong field ligand, right? It is for this reason only, because it can have both sigma character as well as pi character. And again, that can be of two types. It can be either from metal to carbon or from carbon to metal, right? It depends what kind of electronic configuration I'm going to have for the metal, right? Okay, so looking at the stabilities, okay, so if I look at the stabilities, there is only one criteria, people, right? So what you have to understand is stability will be directly proportional to the ability of the metal to donate electrons, right? It is the ability of the metal to donate electrons. Okay, in the sense that from the d orbitals of the metal to the pi star of the metal carbon, I mean carbon, right? So that ability is what is going to define the stability, right? Because eventually you will see that carbon is going to form a bond with metal, right? But if at all both the things are going to happen, say I can have a double bond kind of picture, like you can have this kind of picture coming, M double bond C double bond O. Say one bond going from metal to carbon, the other bond coming from carbon to metal. So obviously this makes the molecule more stable, isn't it? Because of more bonding interactions, right? So that because this eventually is going to happen, carbon to metal is eventually going to happen, right? But metal to carbon, if it happens, that right, that is going to bring in more stability because more bonding interactions are there. Okay, right. Now you don't have to worry about what kind of metal should I have and all that. It's pretty simple, guys. If I have to tell you, this is just one thing you have to look at. The thing is, its stability is directly proportional to the negative charge on the metal, right? Negative charge on the metal. Obviously, if I have negative charge, means that I have excess number of electrons, right? Excess number of electrons. For example, if I consider three compounds like this FeCO5, right? And say I have MnCO5, say plus, and say vanadium CO5 minus. Okay, now if I have to arrange them in the order of stabilities, okay, these three compounds, this kind of question came in JEE mains also. I think last year JEE mains it came. I think this exact question came. I'm not right. Okay, so if you have to arrange them in the order of stability, right? As I told you, more and more negative charge on the metal, more and more waste stability for the metal carbons, right? Now you see here the oxygen state of iron is 0 because it's a neutral compound. right? And here, if you check, it is going to be +1 for manganese. And here, if you check for vanadium, vanadium is going to have a -1 oxidation state. So obviously, first rank goes to this, second rank goes to this, and the least stable of them all is going to be manganese. Manganese with a carbonyl CO. Okay, so hope you understood what I'm trying to say. You have the stability is going to be directly proportional to the negative charge on the metal, right? So here I have negative charge, here there is neutral, here there is positive. So the most stable one is this, the next stable is this, and the least stable is the one which is going to have a positive charge on the metal. Okay, right. Now one last thing, right? Oh, we have to see. We were actually seeing what? We were actually seeing isomerism. Oh, I diverted. Okay, no issues. We have already completed structural isomerism, isn't it? So we just have to see geometrical and optical. That we'll see anyways. Okay, fine. So next thing is about the color of a coordination complex, right? Please understand, guys. How do you see color is a very big question, right? So it's pretty simple. Whatever you see are colored, right? Are actually are going to absorb some amount of electromagnetic radiation in the form of visible light. Okay, so I have some substance, right? So that substance absorbs some amount of electromagnetic radiation. So what happens? Obviously, if it is going to absorb some amount of energy, right? The electrons in the ground state can go to the higher energy state. Correct, right? The electrons in the ground state can go to the higher energy state, and they will not be able to stay there for a longer amount of time because it's unstable, right? So what will they do? They will come back to its original or whatever the ground state possible, right? Now obviously when you want to go from lower energy level to higher energy level, you need to supply energy, and if reverse happens, that is when the electron comes from the higher energy level to the lower energy level, energy would be released, right? Now that energy, if it falls under your visible spectrum from say 400 nanometers to 700 nanometers of wavelength, you will see that that particular molecules are colored. Hope you understood the picture what I'm trying to say. Absorbing energy, going to higher energy level, coming back, at that time you will see that the energy is going to get released, and that energy, if it falls under your visible spectrum, then you will see that the color of whatever the type of wavelength is going to emit out, that color you will see. Okay, right. So in coordination complexes, right, how are we going to determine it? It's very simple. It's very, very simple. Most of the coordination complexes are colored. Most of them, right? Few of them will not be colored. I'll tell you what will not be colored. When you have a D0 configuration or when you have D10 configuration, right, these molecules will not be colored. D0 configuration or D10 configuration, these molecules will not be colored. Why? Obviously, because D10, if I have, right, sorry, D0, if I have, that means there are no electrons to go to the higher energy state. D10, if I have, even the higher energy states are occupied, right? There is no, or I would say all the electrons are paired. Generally, if the electrons are paired, or like taking them out of the pair and then making it undergo the excitation is very difficult. Okay, right? So when you have D0 configuration or when you have D10 configuration, right, you will see that they will generally not be colored. Okay, but there can be cases where, yeah, when I have D10, D0 not possible at all, but when I have D10, actually for D0 also, right? So basically for color, for in your level, I have only one criteria. I should have this DD transition, right? From one lower energy d orbital to a higher energy d orbital, the electrons has to get transferred. If that happens, yes, the molecule will be colored, right? But if you go to higher levels, right, if you go to maybe college level chemistries, you will see that this is not the only criteria, right? DD transition is not the only criteria. You have something called as charge transfer mechanisms, right? Charge transfer. Right now, this charge transfer can be of two types. It can be metal to ligand charge transfer, M to L charge transfer, or it can be L to M charge transfer. Basically, okay, if I want to speak about it, M to L transfer will have when I have D10 configuration. Metal have excess number of electrons, right? Now that will donate it to the ligand, and there the excited state, the electrons can go to the excited state. So that way color is possible. Or say when the metal has D0 configuration, it has empty orbitals, right? So in that case, the ligand can give electron to the metal and then it can go to the higher energy state. Okay, so that's what it called LMCT or MLCT, metal to ligand charge transfer, or ligand to metal charge transfer. So that way also color sometimes is possible. But again, too much for your level. What you have to know for your level is when you have D0 or D10 configuration, DD transition is not possible. So the molecule will not be colored. Is that okay? Right? Fine. So that is about your organometallic complexes. Now we'll move on to your isomerism. Okay. Is the people number of people increased? Oh, we have 4. Good. Okay. Right. So moving on. Right. So next we'll go for your stereoisomerism. Right. So first we'll talk about geometrical. Right. So again, in geometrical, you have to see 3 things: whether tetrahedral complexes, square planar complexes, and octahedral complexes. Okay. Right. So first thing first, what you have to know first thing is tetrahedral complexes do not show geometrical isomers. First thing you have to understand, whatever be the complex, right? Whatever be the type of complex, whatever be the type of ligands it has, right? Tetrahedral complexes, we cannot show geometrical isomers. Now the reason is pretty understandable, right? Say now if you can compare what kind of geometrical isomers is going to exist in organic compounds, you see obviously I need to have a C double bond C, right? So what you understand is these 4 bonds I have here should be on the same plane, on the plane of the board, or wherever the plane of the paper which you write, right? So these bonds should be there on the same plane so that I will be able to interchange them, right? If they are not on the same plane, I cannot call them as geometrical isomerism, but I will call them as what kind of isomers? If I have a C single bond C, then also geometrical isomerism, sorry, not geometrical isomerism, some isomerism exists, not structural isomerism. What is the isomerism there? I call it. Obviously, you see there are going to be bonds going towards you, coming away. All these things are going to happen, right? So in that case, also I have an isomerism. What is it called as? Okay. So if I have, I hope you studied about cyclohexane. Cyclohexane, I told you have dash number of, or it has all these chair, boat, half boat, all these things are called as what? What are they called as? They're called dash of cyclohexane. What are they called as?
Conformers.
Correct. They are conformations of the particular molecule, right? So what you have to understand is the isomerism is called conformational isomerism. Whatever other than C, like your geometrical isomers, optical isomers, your structural isomers, all these comes under the term called as configurational isomerism, right? But this, because of CC bond rotation, if you're gonna have any orientation difference, right, that comes under conformational isomerism. So all these chair, half chair, boat, all these things are called as conformers of cyclohexane. Okay, so anyways, so that's the same reason here. Now this geometrical isomerism is not possible in tetrahedral complexes because you know how the structure is going to be. It is not a planar structure. Okay, right? Fine. Next, what you have to understand, when I go for square planar complexes, right? Now, square planar complexes, what you have to understand is obviously exactly what you had in organic chemistry, cis and trans. That's the kind of thing I'm going to have here also. Okay. So now what you have to understand is you have to understand what are these cis and trans positions. So not carbon, metal. Okay. So what are these cis and trans positions? So please understand 1, 2, 3, 4. If I write, right? So please understand 1, 2, 1, 4, 2, 3. What else? 3, 4. All these are cis. Okay, 1, 2, 1, 4, 2, 3, 3, 4. Like this, all the adjacent positions, right? All the adjacent positions are going to be cis positions, right? Now, obviously, trans you can understand 1 and 3 and 2 and 4 are your trans position. Okay, right? Fine. So that is the first thing you have to know, right? Now, what are the kind of complexes which will show geometrical isomerism, which will not show geometrical isomerism under square planar complexes? That we'll see. Okay. Say what and all will not show. I'll tell you first. Say first thing is when you have Ma4 kind of complexes, that is M with 4 same type of ligand, MCl, Cl, 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 something like that, right? This will not show because we already know. We can just correlate what we studied in geometrical isomerism of organic compounds. We know that the 2 bonds on each carbon should be different, right? Only then I can speak about it, right? So same thing works here. So all the 4 are same, or if say Ma2B2, A2B2 will show A2, oh, A3B, sorry, A2, A3B, say, or I can have say MAB3 or MA2A3B is going to be same. So this kind of complexes are not going to show geometrical isomerism. Hope you understand why. We will not be able to visualize this in trans if you have these kind of complexes, right? Okay, what other things will show? Will be say Ma2B2. Obviously, you can have, right? Ma2B2, I can put AA cis or AA trans, right? Or I can have Ma2BC kind of complexes, 2 ligands same, 2 ligands different. Again, I can have cis and trans. Again, we have to speak with respect to what you're speaking. I can have A cis with A or A trans with A, right? And accordingly, it will be different, right? Say I can have structures like this: A, B, and C. So you see, B and C are trans, A and A are trans, right? Or I can have say A, B, C. So you see, A and A are cis, B and C are cis, right? So like this, I'll be able to come up with so many structures. You don't have to worry about how many I'm going to have. All you have to know is whether that particular molecule will show geometrical isomerism or not. And for your level, that's enough. That's enough, right? Whether that molecule will show or not is important, but how many such geometrical isomers are really not important for you. Same goes with optical isomerism. Whether it shows or not is important, but not how many it shows. Or the other types, that all doesn't matter for you. Okay, right. So this first class doesn't show. This is okay for me, right? Because I'll be able to visualize, right? Moving on. And obviously the next part would be M, A, B, C, D, 4 different types of ligands, right? Now I can have so many types of isomerism here. I mean, so many numbers of isomers can come with respect to A and B are sister trans, or A and C are sister trans, or A and D are sister trans, B and C, C and D. So many combinations can come, right? I would say if you look at all the possibilities, you will be maybe getting 3 isomers for this. But again, if you want to remember the numbers or not remember the numbers, okay. Next, when I go for bidentate complexes, now you saw till now all A, B, C, D, whatever you're writing are monodentate ligands, right? Say if I have didentate ligands, please understand I can have say MAA. I write it like this: MAA twice, right? MAA twice means what? I should have total coordination number 4. This has a bidentate ligand, so I require only 2 of that. Right? Totally 4. So 2 didentate ligands or bidentate ligands, whatever it is. So this will not show geometrical isomerism. For the same reason, why MA4 will not show. Right? But you have seen certain bidentate ligands are unsymmetrical ligands. Right? What do you mean by unsymmetrical? Say something like, say I have NH2, CH3, CH2, CH, or something like this. Something like this is unsymmetrical, right? Even though this is bidentate, this and this can coordinate, right? This is not a symmetrical species. But if I have, say, ethylene diamine or ADTA, right, all of them are going to be symmetrical ligands, right? So at those times it will not show. But if you have of the type MAB twice, now when I put a bracket, that means it's a bidentate ligand. So when I have MAB twice, so definitely this can show geometrical isomerism. Okay, right, fine. So that is about, I think, your square planar complexes. Tetrahedral complexes are not going to show, right? So that's about square planar complexes. Now we'll go for octahedral complexes. Okay. Now again, we have to know what is this position, what is transposition. I think it will be pretty easy to understand. Say if I have A or a metal, okay, right? Say I call it 1, 2, 3, 4, 5, 6, right? So I'll tell you what are the trans positions. All the other positions are going to be cis positions. Okay. Now trans would be 3 and 6, this and this, or it can be 2 and 5, this and this, or it can be 1 and 4, this and this. That's it. Okay. All the other cases, all the other pairs you take, it is not necessary that I need to have only adjacent side. Say if I look at cis positions, say these two are cis, 6 and 1 are cis, 6 and 2 are also cis. Okay, either directly one adjacent group or the alternate one. Both of them come under cis category. Okay, and if at all is going to be exactly opposite in the form of a square bipyramidal geometry, then it is going to be coming under trans category. Okay, again I repeat, 6-1 as well as 6-2, both are cis positions. Same way, 1-2 and 1-3, both are cis positions. Okay, either directly adjacent or alternate ligands can be cis positions, and the exactly opposite of the cases will be coming under trans type. Okay, right. So this we have to know. So we'll see what kind of complexes will give, what kind of complexes will not give. Right. So obviously what you can understand is MA6, MA5B are really not going to show. Okay, right. But if I have MA4B2 kind of complexes, or say MA4BC type of complexes, they will definitely show geometrical isomerism. Right. If at all, I can show you if you want. Say if I take MA4B2, right, now I can put both the B's trans to each other, right, or I can put both the B's cis to each other. Say B, okay, no issues, I'll put B here, A, and A. So you see this B and this B are cis to each other. Okay, right, fine. So you can understand how MA4B2 or MA4BC, right, shows geometrical isomerism. Okay, right. Next thing is a little different one. So when you have, so this will show. Okay. Next, if you have MA3B3 type of molecules, right? So here I will not call them as cis and trans. Okay, I will call them as two, like I call them as facial and meridional isomers. Okay, facial and meridional isomers. But let me tell you how it works. Okay, so one case can be you can put all the A's together and all the B's together. Right, all the A's together and all the B's together. So what I can understand is I will be able to easily form a kind of a face. A triangular face can be formed on either side. Okay. Now this is what is called as your facial isomer. Right. Now, if at all you don't understand how this face comes, please understand that if you put all the A's consecutively and all the B's consecutively, that comes under facial isomer. Facial isomer. Yeah. Right. Now, if you put even if one of them to be just ulta, say in the sense, if I put it like this, M, B, A, say something like this, B, A, P, something, right? You see, they're not consecutive. Whatever type of things you do, right? If you just make one of them to be not consecutive, like A together, B together, it's not like that here. Now, this will come under meridional isomer, right? Facial isomer and meridional isomer. That will happen only for this kind of complexes, M, A3, B3. Okay, right. So that is about facial and meridional. Moving on. If I have M, A, B, C, D, E, F, all 6 different kinds of ligands, definitely it is going to show, right? And you will see that 15 such possibilities are there, right? Again, you don't have to remember the numbers. If you want, if you can remember, right? So 15 such type of things, isomeric forms exist. Okay. Now the next one, if you have M, A twice, B, C, or MAA twice, B2, that is A is a didentate ligand, 2 different ligands, A is a didentate ligand, B and B2, again 2 same ligands, B, monodentate ligand, right? So again, they can show geometrical isomerism, right? They can show geometrical isomerism, right? If you want, you can check. You can just put them, you can just try to put B and C cis together or B and C trans together. It will work. Same way, both B cis together, both B trans together, it will work. Okay, right. Next. Yeah, that is about, oh, one more thing. If I have M, A thrice, I have 3 didentate ligands making coordination number 6, right? Obviously, this is not going to show, right? But if I have M, A, B thrice, in the sense if it's an unsymmetrical bidentate ligand, definitely it will show. Okay, so you can try. If you can just try to put it in the paper, you'll try to get it. This will not show, but this can show cis and trans easily. Okay, so now you saw what and all are the cases which will give geometrical isomerism, which will not give geometrical isomerism. Tetrahedral complexes will not give. Square planar, I have M, you can check it, M ABCD will give, MA2BC or MA2B2 will give, right? MABCD, I already told you. Yeah, those are the things there. And obviously, if I have a MAB twice kind of thing, an unsymmetrical bidentate ligand and square planar complexes, that will give. And here you saw in octahedral complexes, you saw how is it happening. Okay, right. So that is about your geometrical isomerism. Right. Now we'll see how your optical isomerism works. And yeah, one more thing I wanted to discuss. So now today I'll be completing coordination compounds, and after that I have electrochemistry one day, kinetics one day, so solid state one day, solutions one day, 4 important chapters that we have to do. And other than that, I have surface chemistry and metallurgy, like not so important, but still we have to do it. How do you want to do this, guys? Like we have almost, including after this, I have almost like 4 days, because if we kept 15th as the deadline, or say even if we take 16th, I have 6 chapters and 5 days. So 1 day or 2 days we have to go for some little more time. How do you want to do it? Any suggestions you have? Because now that your school also have started.
So what and all do we have to complete?
We have solid state, solutions, electrochemistry, chemical kinetics, this thing, metallurgy and surface chemistry. Everything one day.
Sir, can you teach metallurgy, because we have no idea about that chapter.
I will teach you metallurgy, not a big deal. That's going to be, questions also will be very less, but it's going to be purely theoretical. I'll teach you. No issues. That
Sir,
can be done.
what about polymers, sir? Because in all JEE papers, at least one question coming.
Polymers, what I'll tell you, say you read your NCERT textbook, right? So it's pretty understand. Maybe I'll tell you what are the mechanisms of polymerization, right? I'll tell you how the mechanism happens. But other than that, you just have to know the names. What is the name of the polymer? Say Teflon, right? In that Teflon, what are the monomers, right? That alone you need to know. You need to know. That's it. Like I just have to give you a table. You can make the table of your own. Make one. I would say 4 columns you make. One is the name of the polymer. What are the monomers present and the uses. This alone you make for yourself. That's it. Other than that, nothing can be asked, right? And what type of polymer is it? Is it a addition polymer or it's a condensation polymer? You understand what you mean by addition polymer and a condensation polymer. Condensation polymer means 2 things will come together and one thing is eliminated, just like H2O or HCl, something is eliminated. Addition polymerization means they just add, nothing is eliminated.
Sir, so polymers are easy, sir.
Polymers are very
basic
easy.
questions, sir.
Basic questions. Even if they ask you, they will give you the polymer and ask you what are the monomers present, or say what are the uses of this polymer. Only 2 questions can be asked, nothing else. Okay.
Okay, sir.
Sir, should we study environmental for the exams?
No, please. Just I can questions last year. One question came, right? But is that chapter there for your NCERT for your board exams?
No, sir.
It is not there, polymers is not there, and environmental is not.
Oh. Then I would say what I would really suggest is leave that, because you might get one question or no question, and for that you have to remember so much. You have to remember, and there is no logic, right? For example, if they ask you, you can have different types of. It's all about drugs for the medicines you use, right? So it will be, say, antidepressant drugs, antihistamine drugs. Say I have antiseptic drugs, antibiotics. So all these kind of things you have to remember some names, right? Say for example, I don't remember. Actually, I'm in this field, but I don't remember, because I really, if all I want, I refer it. That's what I do. Remembering it is such a headache. There are a lot of other things you can remember. Actually, it will be useful where you can get some marks, right? So, but again, this is going to be either fully coming or nothing you get. That kind of gamble it is. Okay, so I suggest you study everything else, and maybe just before you go for the exam, just go through your NCERT and go. Just remember the names. Chloramphenicol will be an anti. I don't remember. I just remember chloramphenicol. Say bithionol will be an antiseptic, right? Bithionol will be a component of Dettol, right? So there's something called as broad spectrum antibiotics, narrow spectrum antibiotics, something. Broad spectrum antibiotics can work on different types of bacteria.
Sir, chloramphenicol is an antibiotic, sir. I just googled.
Antibiotic. Okay, antibiotic. Erythromycin will be a anti-fever drug. I don't know what you call it, right? So yeah, so like this, just remember the class of drug, what type of drug is, whether it's an antiseptic or antibiotic or whatever it, antihistamines or whatever it is, and remember the name. That's it. That's all you have to remember. But again, I would really suggest do not waste your time on that. You have a lot of good questions, lot of good areas. You'll get at least 3-4 questions. Chemical bonding is one. Electrochemistry, you might get 2-3 questions. Chemical kinetics will get 2-3 questions. Organic is very important. So many organic reactions we have. Oh, we have amines also. Oh my God. Okay, amines we have, and you have to do problems on that. So guys, tell me, how do you want to do it? See, this chapters I really want to touch, right? I definitely teach amines. I have not, I have to do problems on that. So, and then I have to do problems on electrochemistry, because I don't know how much, whatever you know, solutions, solid state, and chemical kinetics. These 5 chapters I have to touch somehow, right? Other than that, metallurgy and surface chemistry, at least we can do it at the last. Even if it's going to go beyond the deadline, I'm okay with it. But these things we have to do. Today is 11th, and we have almost 4 more days: 12, 13, 14, 15. Maybe, are you okay with Sunday having? No, Sunday I will be busy. Sunday 4 to 5 morning. Yeah, we can have Sunday. Can I have 3 hour session? Morning 1.5 hours, and evening 1.5 hours. Is it okay?
Okay, sir.
How about others? Are you okay, guys?
Yes, sir.
Okay. So if you can do that on Sunday, maybe that will help. Fine. I'll plan what we can do.
Sir,
Fine.
So
So
what
no,
about
sir,
biomass?
even electrochemistry is manageable, sir. Only chemical kinetics, only this activation energy equations, I have no idea.
that will
It's
see.
been deleted for us.
Yeah, electrochemistry, I think, yeah, as you said, it's pretty easy. If you just know the formulas, if it just give you the formula, then you have to apply it. The most important thing is Nernst equation, right? Nernst equation, then you have to go for Faraday's laws of electrolysis. You have 2 laws questions coming from that. Again, that is very easy. Then your conductivity, molar conductivity, limiting molar conductivity, Kohl-Roche's law. What else? What kind of other problems are there? Yeah, that's it. And depending on the reduction potential values, you arrange them in the order of reducing powers, oxidizing powers, ability to get reduced, ability to get oxidized, right? So those are the different kinds of question. Chemical kinetics, yes, chemical kinetics is little that way, conceptually little more to understand. But
Yes, sir,
again,
can we
problems.
also do some problems on Arrhenius equation, sir? That's related for
Yeah,
us.
every problem will do. If I do problems, I will touch everything, not only one
Okay,
part.
sir. Okay.
Every part will be touched. Yeah, that is not a big deal.
No, sir, can you focus on that because that's completely deleted for us.
What? Seriously?
Yes,
That
sir.
part is entirely deleted. What is
Only
the
till
most
pseudo first order we have, sir.
Anyways, so like that particular thing, Arrhenius equation is very, very important in the sense for it is most interesting also. Okay, I don't know why they took it out. Fine, no issues. We'll see. Fine. So moving on to this optical isomerism. Right. So in optical isomerism, first let me tell you. Okay. So first about your square planar complexes. Right now, square planar complexes are not going to show optical isomerism. Right now, why is it like this? It's pretty easy to understand. It's just the same reason why it was able to give geometrical isomerism, because it is going to be in the same plane. Right. So please understand the instrumentation of checking whether the compound is optically active or not is pretty much same to the organic chemistry. I have a normal light. I pass through something called as a polarizer. Now I'm going to get a plain polarized light. I know plain polarized light will have vibrations only in one direction. Right. Okay. So this plain polarized light will be focused on a particular molecule, and I look at the output. Right. So in the output, if I see that the plain polarized light has a little deviated towards right or towards left, I say that that particular molecule is optically active. Yes. Right. Now, for you to have the rotation happening, right? If see, I don't know whether you are able to get it. If the plain polarized light is going to come like this, right, and this molecule is planar, right, and you will see that there will actually be no change. There will actually be no change happening in the plane polarized light. But if at all this molecule is not planar, one thing coming towards this side, other going inside, and all that, this will have variable interactions because of the elegance present in different planes, and that might be a cause that the plane polarized light is able to rotate. Okay, so generally square planar complexes will not show geometrical isomerism. Okay, right? So that you understand. So it's like exactly opposite of your geometrical isomerism. Square planar will show, tetrahedral will not show. Here square planar will not show, but tetrahedral molecules will show, because obviously they have 4 different bonds, in the sense that all of them are different planes, right? So that is going to help. Okay, so here so first, if you go for tetrahedral complexes, Okay, so remember, a geometric isomers is important, optical isomerism is not. Okay, you don't have to worry about it. Okay, so right, the only possibility that any type of tetrahedral complex can show geometric isomerism is this, of the type MABCD. It's just like a chiral center, is it not? Like tetrahedral carbon, why, when will I say it is chiral? When it has all the 4 groups to be different. Here also the metal should have all the 4 types of ligands should be different for it to be optically active. All the other stuff, all the other things actually will not be optically active. Okay, right? Okay, next one, next quarpinar over. Yeah, next we'll go for octahedral complexes. Right, now octahedral complexes, okay, so first one is MA4B2. So in this case, I know they will show both cis and trans, and both of them will be optically active. Right, you can ask me, sir, not all 4 ligands are different, but what I can understand is in one plane there will be certain type of molecule, another plane there will be another type of molecule. So there is a chance for the plane polarized light to get rotated. Okay, right? So MA4B2, both cis and trans molecules will show geometric, I mean optical isomer, and MA3B3 does not form. MA3B3, you have 2 here, both facial and meridional. None of them will show optical isomerism. Again, for the same reason, because in one plane, same set of molecule, there'll be a plane of symmetry. Basically, there are 2 conditions for you to have optical isomerism. One is chirality. The other one is there should not be any plane of symmetry. So this will have a plane of symmetry, both facial as well as meridional. Okay. Next. Under this, obviously, the obvious type would be MABCDEF, right?
Sir,
So we,
actually, how does meridional have a plane of symmetry, sir?
the is over. Okay, so if you look at this, if I take this as a plane of symmetry, don't I have a plane of symmetry? Or okay, maybe in this case you're not able to see, but I can put it ulta also, isn't it? Right? Or if I write, even if I take this as the plane of symmetry, but again this will not work. I have D here, A here. If I put B here, so what you're asking is right. Yeah, they, or what kind of plane of symmetry are they talking about? Once again, I take this A, B, B. Yeah, this has no plane of symmetry. A, B. This has, right? If I take this one, AB this side, AB that side. Or you can see it like this. Maybe you will tell that this is AB and this is BA, right? So when the plane polarized light is coming, maybe say it is when it meets this point, it is rotated by say some 5 degrees to the right. Okay. Now when it crosses here and comes to this side, can I say this is going to nullify it? Say again, this is going to rotate that plane polarized light towards left by 5 degrees. So what will happen? The net rotation is 0. Are you able to get my point?
Yes, sir.
Okay, fine. Cool. So that is that. And what about MA2B2C2?
Sir, that means even for facial also we took a similar plane of symmetry only, no, sir. Then we got AA and BB.
In facial, we're not going to get it. In facial, that is actually going to have a plane of symmetry. One second, let me check. If I take this as the plane of symmetry, you have one AB, another AB. Yeah, this exactly has a plane.
Yes.
This as the plane of symmetry. Okay, so actually there is a entire different branch of chemistry which study. There's something called a symmetrical and asymmetrical chemistry. This is all that the chemist works on this only. This is a very small kind of structure, but if I have a very complex kind of very big structure, you like understanding what are the planes of symmetry, what are the points of symmetry, what are the asymmetric points, and all that itself is a different field of chemistry. Okay, fine. Anyways, so moving on. So when I have M, A, B, C, D, F, I told you we'll have 15 geometrical isomers. All of them will be optically active. Right, so can I say there will be 30 optical isomers, because each of them will exist in D and L forms, plus and minus. So for each 15, 2 of them will be there, so totally 30 optical isomers will be there. Okay, right. Next, when I have
Sir, we are using the 2 power n formula only, sir.
2 power n,
Like, because there's only one chiral.
yeah, but again, do not go for the numbers. Numbers will be very complex. See, I am telling you a general case, but in this case itself, due to some of the ligands, you will see one or two, one higher or two higher or three, one or two lesser the numbers. That's why I'm not telling you anything. That's why I'm not talking about the numbers at all. Okay, now this is very easy, because I told that I have 15 geometrical isomers and all of them are optically active, in the sense that each of them will have DNL, like 15 times totally optical, 30 optical isomers. But again, you don't have to worry about the numbers. Okay, what in the exam you are going to do is that you are going to take the coordination complex and fit into any of the types which you have seen, and if it fits, you know whether it's going to be optically active or not. That's how it works, right? Fine. So Ma2, B2, C2, you have, right? So in this, what you have to understand is the cis form is optically active, but the trans form is optically inactive. Okay, cis form will be optically active, but the trans form will be optically inactive. Again, because trans form is going to have a plane of symmetry. You can check if you want, just draw it and check, right? So the trans form will have planar symmetry, so it is not going to be optically active, but cis will be optically active. Okay, right? Any other thing which I have to tell you? Okay, now I'll tell you one thing which will not show geometrical isomerism but will show optical isomerism. There is a special case like that. Right, so that is MAA thrice. Okay, now MAA thrice is optically active, but MAA thrice will not show any geometrical isomerism. Okay, this we saw that time. Okay, then same way, if I have MAA twice B2, so here also I'll have cis and trans. Cis will show, trans will not show. Okay, yeah, and there is one just exemption, and I have MA6. Obviously it is not going to show, but if I have M with EDTA, this will be optically active. Okay, generally MA6 compounds is not going to show. This is MA6 means single 6 numbers of monodentate ligands. Okay, now they are not going to show geometrical isomerism, but if I have EDTA, which is a hexadentate ligand, that will show optical isomerism. Talking about optical isomerism, sorry, this is not going to show optical isomerism. The only MA6 type of compound which is going to show optical isomerism is this, when you have metal with an EDTA complex, because EDTA is going to be a hexadentate ligand. Okay, so yes, these are all things which you have to remember. Okay, right. So I would say just solve as many as questions as possible. Like again, questions coming from this are very rare, right? But even if you get, just try to put them in the system, any of the systems we have seen, and try to get the answers. Okay, right? What is the time? Time is 6:10. Okay. Fine. So that's about this chapter. Anything else I missed? No. Okay. Right. Fine. Okay. What chapters you want to start, people? Next. Kinetics.
Okay, sir.
Oh wait, we will do some orals. We'll not start anything today. Maybe we'll do some problems that I forgot. Just give me a moment. Okay. Okay. Say I have 4 options. Okay. So in this 4 options, tell me which will not show optical isomerism. Which will not show optical isomerism.
Sir, I have a doubt. Like
Yes.
for A and B, sir, like A, B, C, does it actually matter? Like for example, if it's ADT or some ligand like that, does it actually matter, or like only the geometry, only the number of A and number of B, number of C only matters?
Yeah, that whatever I told you, the ways, MAB, say maybe twice, whatever. that thing alone matters. What type of ligand you have, I told you only one exemption, the DDTA. That is the only exemption. Other than that, you don't have to worry about it. Just look at the type, look at the
Even
ligands.
if ammonia with strong field, weak field, you don't need to care about.
Nothing matters. Nothing.
Okay.
Okay, right. So what is the answer to this question?
C, sir.
Yeah, obviously. What is the type? MA3D3. I told you that it will show geometrical isomerism, but it will not show optical isomerism. Both facial as well as the meridional isomers. So remember, MA3B3 will form facial and meridional, and none of them will be optically active. Right? So C is the correct answer to this question. Which will not show optical isomerism is this. Okay. Any other good question? Fine.
Sir, at the end of the class, can you tell how to study organic chemistry? I'm not.
See, organic chemistry, how to study. Okay. So first things, you have to know all the reactions. Like I think now at least you know what are all the reactions, you know what are the reactions, you know what are the products, what are the reagents. At least by this time you must have been comfortable. I don't think that will be a problem. If that is a problem, then maybe you have to sit and study, right? And but if you
No,
already
sir,
finished,
that's not the problem for me.
that's what.
I'm
Then
able
maybe
to figure out what's the product and all, but only
okay.
during the mechanisms or something like that. And I'm weak at stereochemistry, sir.
That's what I'm
I
telling. So
confused between the isomers, EZ, RS, like I always get confused. So not sure how to study.
I understand. So what I do, I don't know which institute you're going, but all these institutes, what they generally do is in their books or whenever they conduct tests, they will actually prepare a very tough type of questions. Okay. So what you do is like you first start with previous year questions, right? Previous year questions you try to solve first. All the previous year questions of all the organic, whatever you have, just try to solve, right? That's the first step. And after that, maybe take a test series. And in that test series, you go for it. Do not try to solve all these questions are given in their booklets, whatever it is, whatever the be the institute, whether all the big institutes, Akash, Fiji, or whatever it is, right? They will try to scare the students. Now that is where their way of making the students study. But I really don't agree to it. But anyways, so what you do is you start with the previous year papers and see how they're answering these questions, right? And then you go for any test series. See, organic is one thing that, as you said, even though you know the reaction, you know the mechanism, right? But sometimes you will not be able to get the output, right? So, but what to say for but that will eventually come. You know the basic stuff. You know the reactants, products, reagents, and the mechanism. Getting the product out, maybe you will find it little distinct because say when I give you 3-4 sequences, right? I gave you 3-4 reactions put together, or say I give you the reactant and product and I ask you what is what is the reagent used. Now those kind of questions will only be difficult. If you know only one reaction, 90% of times you'll be able to get it, right? So all I suggest is you don't have to worry about now the theory part. Just take any number of questions. Go for first you solve the previous year papers of all the organic chapters, right? And you maybe that itself will give you around some 500 questions. Maybe if you start last 30 years, if you solve all the questions coming from organic, that itself will give you around 500. I don't know. I'm just giving you a rough number. So many questions you'll get, and you will eventually know the answers to this because I don't know whether you have that book or else buy that book. Last 30 years, chapter wise questions from JEE Mains. Last 30 years, chapter wise along with solutions they will give. Okay. So by that is I think Aryan publications or so many other publications are also there. Whatever publication you want, you buy, but make sure you have the solutions along with you that time. I mean, in that same book, that you do, and then you go for any test series. Test series, or maybe there are certain institutes give minor test series, then major test series. Minor test series will contain either only organic, or only physical. You take only the organic chapters and then you do it. And then, or I would say, but you don't have much time now. So what I would strongly suggest, finish your previous exercise, previous questions, and then directly go for full portion test series. Okay, obviously you will have 30% of organic in that. 1/3, 3 questions, 1 question will be organic. That's the plan, right? So again, that way you'll be able to get. And one more thing is, you can always share it with your friends, right? If at all you feel that some of your friends are like-minded, right? Organic chemistry is always fun to do along with friends, right? I don't know what kind of fun do you do. Even I have never done it, but now that I've go to college, now I've seen people doing it. It actually works, right? You like whatever the small mistakes you do, that can be pointed out. So that way also you can develop. But the best way to do is going to do by problems. Ask many as problems, get well versed with it, then go for it. That's it. That's the best way. Okay. Right. Yeah. So what question I was thinking about is this question. Okay. Okay. So the question is, which of the following will give geometric isomers? Which are capable of giving geometric isomers? Yes. Any answers? Answers?
Sir, all of these.
Yeah. That's the answer. Right.
Sir,
So
for
don't you
first
see
one,
that
how? Sir, for A, how,
MA,
sir?
Ma2B2, this will show, right? PTCl2 NH3 twice.
Sir,
Ma2B2
sorry,
type.
I couldn't get that, sir. Sir, can you show the structure for MA to B2?
Oh, okay. So Ma2B2, if I have to say now, I can have AA trans, BB trans, or say
Oh,
AA
now I got it,
cis,
sir. Yes, sir. Yes, sir. Yes, sir.
BB and
Cis and
cis.
trans. Okay, sir.
Right? Geometry isomers is what you're talking about. And this is of the type Ma2BC, is it not? Palladium, 2 chlorine, bromine, and iodine. And this is of the type MABCD, right? So all of these will show geometric isomers. Okay, right? Fine. Next question. is so I have option A COF6 3 minus, option B CONH3 6 times 3 plus. Both are COs. Okay, both are COs. Option C, you're able to see, right? Option C, yeah, you're able to see. So option C is FeCN 6 times 2 3 minus. Option D is CrNH3 6 times 3 plus. Okay, so these 4 options I have. So I want to know which one is sp3d2 hybridized, right? In which of the 4 the central metal atom is sp3d2 hybridized?
D, sir.
I'm not sure, we can check. Okay, one option is D.
Sir, NH3 is a weak field ligand.
NH3 we consider a strong field mostly.
The pairing won't happen now, sir.
Yeah, pairing won't happen. But again, sometimes strong field or weak field will not matter depending on the configuration. I don't know, this might be the answer. We'll check. Okay, so CO here is in +3 oxidation state, right? So cobalt will have manganese, cobalt, correct? Chromium, manganese, iron, cobalt. So it will be 3d5, 3d6, 3d7, right? So it will be 4s2, 3d7. Am I right for cobalt?
Yes, sir.
No, wait. So it will be scandium, vanadium, titanium, chromium, manganese. Manganese is 3d5, iron is 3d6, cobalt, yeah, 3d7. Okay, so it's 4s2, 3d7. Right, now this is for cobalt fully. If it's going to be CO3 plus, then it would be 3d6 configuration. So 3d6 will be like this. So 1, 2, 3, 4, 5, 6. And F6 pairing is not going to happen. So I should have, okay, that's a d orbital. So fluorine is a weak field ligand, so pairing will not happen, right? So obviously I have to go for sp3d2. So I think this is the answer, right? So CO3 plus, same thing. CO3 plus, if I'm going to have in the presence of NH3, the pairing will happen. So if pairing happens, can I say it is going to be like this? 1, 2, 3, 4, 5, 6. Now you have D1, D2, sp1, p2, p3. So in this case, you will form D2 sp3 orbital. I mean D2 sp3 hybridization. Okay, so A is the answer. Same way for Fe. Fe maybe you can easily see that it is going to be with CN, strong field ligand. Here also you have NH3 strong field ligand, so pairing will happen. So eventually possibilities that you might have inner orbital complex C2sp3, but this is a weak field ligand. So blindly, but again, do not go for this just by seeing a weak field ligand. Don't try to answer the question. You try to do it. You try it. It will not take minute. Maybe for each and everything, it will maybe take you 10 seconds for you to get what is the hybrid if you do it properly. Okay, so yeah, the answer to this question is A. Right. Okay. Next question. All are so see, you know how to calculate the number of unpaired electrons, and then also you know how to, now from this you can say, for example, if this CO F63 minus, if I ask you how NH4, it's not NH4, it's NH3. NH3 is a strong field ligand. How NH3 is a strong field ligand? Again, okay, these are determined by experiments. There is no theoretical concepts to this. Okay, right? Generally, what I can tell you is when I have a neutral ligand, generally speaking, neutral ligands are generally little more stronger than what is that, negative ligands. But again, there is nothing like that. You cannot generalize it like this. All these are obtained from experimental procedures, right? It's all based on how strong is the bond, right? If I have a very strong bond between the metal and the ligand, then I decided it is going to be a strong field complex, and that's it. I told you how I can do it also. It will be helped with done. It will be done with the help of something called spectrometry. That's why it is called spectrochemical series. Okay, don't worry about it. How is this strong field? How is this weak field? For certain things, we can say, for example, if I go for Cn minus CO, all these are actually both sigma donors as well as pi acceptors, right? In the sense that sigma donors means they'll be able to have a sigma bond like this with the metal. And also I told you what are pi acceptors. These are going to have empty pi star. This is also going to have empty pi star. So electrons can be donated into this empty pi. So they can be accepting electrons, pi electrons, or they can be sigma donors also. Okay. So generally, if you have both these categories, they'll be extremely strong ligands. Okay. Right. Anyways, do not worry about it. So yeah, what I was telling is, if I ask you to find what is the magnetic moment, sorry. So what is the magnetic moment of this complex COF6? What will you do? You know, the formula is magnetic moment is root of n into n plus 2, right? N into n plus 2, that n, where n is the number of unpaired electrons. So in this case, you will find that I have 4 unpaired electrons. You will put 4 into 4 plus 2, which is 24. Root of 24, you will find 4.9. Okay, correct. Right? Okay. So like this, you should be finding it up. Okay, right? So I think that kind of questions are only there. Find the, so some question is like this. Find the magnet, like which of the following will have a magnetic moment of 1.73 Bohr magneton. So they gave you 4 options and they asked you which of them will have 1.73 Bohr magneton. Basically that will be what? Root 3, right? Root 3 is what is 1.7. So it should be 1 into 1 plus 2. So which is going to have 1 unpaired electron. That's what they're asking. Hope you understand. So this kind of questions can also come. Pure formula substitutions. And if you know the electronic configuration, one more thing, you have to know what are the group numbers. You have to know what are the group numbers of all the D block elements, or else you will not be able to answer simple questions like this that I already have mentioned, right? Okay. What is the time?
So it's better to know the entire D block thing, sir.
Yes. It's better. All say group 3 to group 12. So 3, 4, 6, 5, 6, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, 3 to 12. 3 elements you have to know.
Okay.
30 elements basically. Or else they will not give you in the question. Like this, only questions will be asked. Simple questions you will not be able to answer. Okay. Right. So I think I need to do some couple of more questions. Okay, that we'll do tomorrow. Maybe I'll just take 15 more minutes tomorrow and I'll complete it. And tomorrow we'll be going for chemical kinetics. Okay, and tomorrow itself I'll be completing it. I'll try to complete it without rushing. Obviously, that is there. Okay. Any questions, people?
No, sir.
Okay, fine. So we'll see tomorrow. And on Sunday, I'll tell you whether we are going to have 3 hours class or not. I'll put it in the group. Okay, I'll discuss with Raghav and I'll let you know. Okay, fine. Thank you, guys. We'll meet again.
Thank you, sir.
Thank you, sir.
What is wrong?
Thank you, sir.